All right, guys, welcome back. Hope you guys had a good weekend. We are now starting chapter 9, and of course, like I warned you guys, chapter 9. Um, and I say warn in a positive connotation. Um, I'll let you guys know, of course, what was to come up, which is, of course, my favorite topic, right? Routing and switching, which is spanning tree, right? And so chapter 9 is going to go ahead and touch on spanning tree protocol concepts, right? From a CCNA level, right? So I'll make sure that I don't, that I keep it there and I don't go any higher or don't miss any information. And if I do, of course, reach out. I'll provide some documentation, resources, of course, do your due diligence as well. Um, let's go ahead and get started, man. Um, with me knowing about spanning tree, I am going to take my time. This is probably going to be a 5 to 6 part session. I'm not going to try to throw everything at you at once because it's a lot of layer 2 information that's going to be thrown at you. So we're going to take our time. We're probably going to stop in the middle of it. It'll probably be a 15-minute session, and we'll go from there. Right. So again, I'll let you guys know as a reminder, always before we start the session, we overlook how the OSI model looks like, and of course the TCP/IP stack. Okay. All right. So the objectives here, right? Um, objectives here, right, is we need to one configure and verify layer 2 and layer 3, right? Ether channel, right? LACP, which is of course new to you guys. Describe the need for and basic operations of RPVST, right? And identify the basic operations of it, right? Identify what a root port is, what a root bridge is, all right? And a primary and a secondary root bridge and how that falls into a layer 2 topology, right? Or a spanning tree, right? And of course, the other port names. Identify the port states, right? Forwarding, blocking, etc., right? There's different types of port states. And of course, port fast benefits, right? We're going to touch on that. So it's a lot of things, right? With, 5 different things, but within these 5 things, there are many other little things, right, that we need to break down, take our time with, because of course, um, you may see when you do take the exam, you may see things that you learn in here, and probably in some show commands, you'll probably see it within a topology. So you're gonna have to break that down. So let's go ahead and jump in and talk about some theory, and then tomorrow's lab day, I'll show you guys how that looks. Okay. All right. So let's talk about it, right? Let's talk about some basics, right? So without spanning tree, right? Or RSTP, right? Which of course is mostly used now by default, um, out of the box, right? For Cisco switches. Um, Local area networks, right, with redundant links would, if they're all connected, right, but spanning tree is not used. I'm trying to paint a picture. So we have 3 switches, they're not using spanning tree, right? If PCA, right, maybe tries to send right, to send some traffic or send something to PCB, right? What would happen is, right, with these redundant links between these 3 switches, right, them not having spanning tree, they're going to continue to keep sending the same frame, right? Because we're talking about layer 2, right? To a point to where it's going to cause a loop for an infinite amount of time. Okay. But, right, because again, we spoke about the 3 major functions of a switch in the earlier chapters, right? Spanning tree being one of them, right? And here's why, right? With spanning tree, right, it's going to go ahead and do some calculation, and we'll talk about that in the future, about what ports, right, on this, redundant setup, which port to block, right, which ports, which means blocking, mean which ports not to forward frames out of, right, and which ports to forward frames out of, right. And they do this, they just don't do this randomly, right? There's a method to the madness, right? It's an algorithm that goes with it, right? But there's 2 goals in mind that spanning tree is trying to achieve, right? All devices in a VLAN can send frames to all other devices, right? In other words, spanning tree, right, does not block too many ports, right? because of course we block too many ports, right? Traffic can't get out, right? From our traffic can't get from the source to the destination, right? Which would cut off some parts of the local area network. So we don't want to do that, right? And the second goal, right, is frames have a short life, right? They don't last forever, right? So if we go ahead and we don't use spanning tree, it's gonna, and it loops around the network, right? It's not going to, stay alive forever, but it will cause disruption within the network. So we need to make sure we understand the theory and the importance of spanning tree. And this should have told you the reason why this is, and you guys should be able to put together why this is one of the three major functions, three main functions of a switch. Okay. So while you guys are reading the book, right? You guys are probably you're probably going to see and probably ask yourself, well, is it STP or RSTP, right? So when Cisco talks about STP or RSTP in this book, right, it's the same thing, right? They're referring to it as the same thing. So if they say STP, they're referring to both STP and RSTP. Okay, so let's talk about this diagram, right? So we have Bob, right? We have Bob. He's trying to send, he's trying to reach out and talk to Archie, right? And you see that, Bob is sitting off of fast Ethernet 0/13. Okay. And of course, off of switch 3, right? And switch 3 has, redundant connections to all the switches, right? So he has a connection to switch 1, he has a connection to switch 2, and switch 2 has a connection to switch 3 and switch 1, and switch 1, same thing, right? But spanning tree, right, is not enabled in this topology, right? And so we spoke about unknown unicast broadcast. So what happens is, right, if a switch, right, if a switch does not know, right, where a MAC address sits, right, it's going to flood, right, it's going to send that frame to all hosts within a local area network, right, or a broadcast domain, right, VLAN, right. It's going to send it to all hosts that live inside of there, right? And whoever responds, right, it's going to say, oh, okay, hey, I know where this sits at, right? From a layer 3 standpoint, I'm going to go ahead and, I'm going to go ahead and respond back. That switch that the destination sits off of is going to learn its MAC address from a layer 2 standpoint, and it's going to respond, right, to the source saying, hey, I got the host, your destination got your request. I'm going to go ahead and forward it back. Everybody else can, can go ahead and retire, the frames that it received. But this is me talking about if spanning tree was being used. Spanning tree not being used, what we see here is that the frames, right, after it leaves switch 3, it's being sent to switch 2, right? And switch 2 sends it to switch 1, right? And so it's forwarding, right? And switch 1 is sending it back to switch 3 where it originated from. So we see it going, and it's going, right? And so what's happening, right? So what happens is what they call a broadcast storm, right? Meaning that things are going to continue to loop until something changes, right? What is that change? That change being somebody shutting down the interface, which I highly doubt if it's a broadcast storm, because of course you wouldn't have access, right, to the CLI. You'll see something called a traceback, right? It's an error message. It's going to tell you, hey, you can't do anything in the CLI. You can try to press anything, right? Typically, either you're going to do A, reload the switch, or B, break the loop however you do, right? Whether it be pulling out an Ethernet cable, right, out of an interface. That's part of the spanning tree, right? Want to make sure I say that, so that you kill the broadcast one, right? Those are the things that would kill it, right? But this is in a scenario if we did not have spanning tree working, right? But let's talk a little bit more about the storm, right? because what the storm truly does, right, is it causes a MAC table instability issue, right? And I know this because, of course, I've seen this time and time again when quote unquote spanning tree was disabled on a Cisco switch for some people that I help troubleshoot with, right? And so you guys are probably asking, okay, what does this instability means, right? It's a MAC address table, right? It should be smart enough, right? It is, right? But what happens is it's going to do its job very, very well to the point to where it doesn't know where to adapt, right? And so what's going to happen is in a broadcast storm, the switch is going to go ahead and learn, right, those MAC addresses. But what's going to happen is the MAC address tables are going to keep changing, right? Because the frames from the source, right, it's going to change on different ports. So it's going to say, hey, right, if we're talking about switch two, right, let's go ahead and look at switch two on this picture. It's going to receive that frame, right, off of gigabit 0/1. Send that frame out of gigabit 0/2. In the broadcast storm, switch one is going to send that back to switch two, right? And so now switch two's MAC address table is going to say, I received this, right? It's not going to change, right? Because it's all in the same broadcast domain. It's not going to do a frame rewrite. It's not going to do that. In the MAC address table, it is going to put an entry to say which port it learned, right? It learned this MAC address off of. And so it's going to look inside its MAC address table, right? Remember, we talked about that. We talked about the TCAM and everything. It's going to say, wait a minute, I have two entries for this same MAC address on two different ports, right? Right, from Bob. And so again, it's not going to know, what to do, where to go, how to operate, right? And so again, it's going to send it out of gigabit 0/2, but then it's also going to send it out of gigabit 0/1 within the storm. That's why, of course, it is called a MAC table instability. It's continuously changing, right? And so with these looping frames, right? Um, right, and of course these multiple copies of the frames to the destination, right? It's you can cause, of course, that and host to be overloaded with multiple copies, right, of that same frame. Okay. And so we spoke about it. We spoke about an unknown destination unicast, right? Earlier chapters, and of course previously, right? It's going to continue to flood, right? Um, so this is why, right? Spanning tree is needed. It's one of the three main functions, major functions, how I like to say it, so that our local area networks that have redundant connections can operate smoothly and have one path, right, within a network to host. Okay, let's keep going. All right, so we spoke about broadcast storms. Let's go ahead and read Cisco's definition of it, right? Because of course we're going through the exam, right? So the problem, right? And we're going to discuss these three classes of problems caused by not using STP, right? So broadcast storms, right? The forwarding of a frame repeatedly on the same links, consuming significant parts of the link's capacities, right? Right? Short and sweet, right? Make sure you guys remember that, right? MAC table instability, right? The continual updating of a switch's MAC address table with incorrect entries, right? In reaction to looping frames, resulting in frames being sent to the wrong locations. Okay, all right. And right under MAC table instability is multiple frame transmission, right? A side effect of the looping frames in which multiple copies of one frame are delivered to the intended host, confusing the host, right? So this is why we need spanning tree, right? We need it within our networks. And of course, it's used to this day, right? It makes the world go round. And of course, why you guys have to understand it. Okay. So this looks a little better, right? We have one way in, one way out, right? One way to different hosts, right? We don't have multiple ways, of course, that will cause a storm, right? And so what does spanning tree do, right? What does it do, right? We see here, we have something that's different on the diagram from before. right? It's blocking a port, right, to go ahead and break the loop, right? So it blocking that port makes it, you know, makes it to where, frames aren't, there isn't a multiple, multiple frames aren't being transmitted, right, to the host, right? There's no MAC address instability, right? Because there's only one way throughout the spanning tree topology that's here, right? For certain hosts, right? And so let's talk about traffic flow, right? The path of a frame, right? I was about to say path of a packet, right? So we're at Bob, right? So Bob goes ahead and send that frame, right, to switch 3, like we said before, because Bob is living off of fast Ethernet 0/13, right? Switch 3, unknown unicast forwarding, right? It's going to go ahead and send that frame only to switch 1. Why? Because that port that's connected to switch 2 is being blocked now because we're using spanning tree. It's in a blocking state, and we're going to talk about states in the future chapters. Okay, so it's only going to send that frame out of gigabit 0/1. It's going to do the flood, right, all to all S, right? It's going to send that frame to all S, right? Switch 1 is going to go ahead and receive it, right? And it's going to do unknown unicast flooding as well, unknown unicast broadcast as well. It's going to send it out, right? Right. It's downstream, ports, right? Those PCs, and it's going to send it out, right? Gigabit 0/1. It's not going to send it out off the port it receives, right? Because that would break one of the rules of unknown unicast forwarding, right? Or broadcast, right? And so it's going to send it towards switch 2, right? Still not a storm, right? We're still following all the rules, right? And so switch 2 is going to get it. It's going to send it down all its downstream ports, right? And it's also going to send it down to its connection to switch 3. But when it gets to switch 3, that port is blocked, right? So that frame is going to go ahead and be ignored, right? It's going to go ahead and be dropped there. Okay, but it's going to be sent to Archie, right? And with the destination be Archie, Archie's going to receive that one copy. Okay, so there's one way to Archie and one way back to Bob, right? This is a successful converged spanning tree topology. Okay, all right. And so when I use the term converge, and of course you guys read it in the book, I think it totally says convergence, right? It's referring to the process by which the switches collectively realize that something is changing in the topology, right? And that's when they start the fun stuff, right? They start the algorithm, they start doing the calculations, say, all right, here's what I need to block, here's what I need to forward. And this is what we're talking about, port roles and port states and what have you, to create a successful spanning tree topology, right? Let's keep going. Okay, so states and roles, right? What does it mean, right? All of the root, and we're going to talk about a root bridge in the future. Let's just get through this now. And you know what? Let me review this. You know what, guys? Let's not jump because I haven't told you guys what a root is, right? Before we do anything, okay? Before we move forward, let's go ahead and go over, right, what that algorithm is, right? And so algorithm, right? That spanning tree algorithm, STA, what it does is it's choosing the interfaces to be put in a forwarding state or in a blocking state. Okay, so real easy, real way to think about it. When the spanning tree algorithm, performs its duties, right? If it, for any interfaces that are not chosen to be in a forwarding state, it's going to go ahead and spanning tree is going to place those interfaces in a blocking state. Okay. All right. So there are a couple of things, right? Criteria, which is better to say, to where spanning tree chooses whether to put an interface in a forwarding state, right? So reason one, right? Spanning tree is going to go ahead and elect a root switch, right? So that root switch, right? You can think of it as the king, right? The king of all switches within a spanning tree, right? The spanning tree on the root switch is going to go ahead and put all the interfaces, right? Working interfaces in a forwarding state, right? Key topic. It's not listening to the book, but just remember that, right? Each non-root switch considers one of its ports to have at least one administrative cost between itself and the root switch, right? Right, and that's called, of course, a designated port, okay? And that cost, right, is going to go ahead and be called the root cost, right? And that's why that port will be called the root port, right? And so again, it's going, the spanning tree algorithm is looking for the least cost to the root to be able to call that port the root port, right? And that root port, of course, it will be in a forwarding state. All right. If we're looking at switch 3, right? Looking at switch 3, and we see, right, one port is blocking, one port is forwarding, right? We can go ahead and assume, right, we have switch 2. Switch 2 is a designated switch, but switch 1 is the root switch, right? All of its ports is forwarding. We don't see nothing being blocked, right, on its links, right? So we can say switch 3, gigabit 0/1, is the root port to switch 1, right? All right. And so, because again, lowest cost, and we'll talk about cost, more details about the algorithm in the future, right? So one important thing, and of course, this will be the end of today's session, because again, I don't want to throw too much at you guys, right? Is this, right? So many switches, right, can attach to the same Ethernet segment, right? And the term segment means, of course, one connection, right? One connection between two devices, right? That's an Ethernet segment, right? But due to the fact that the links connect to two devices, right? Switch 1 connects to switch 2 and switch 3, right? A link would have, right? That link would go ahead and have a redundant link between that spanning tree topology, right? So switch 1 has a link to switch 2, switch 1 has a link to switch 3, right? So it has two ways to get to switch 2, two ways to get to switch 3. Okay. But, right, if we're going through the process of convergence, right, we picked our root switch, we picked our root ports, right? We also need to go ahead and choose our designated switch, right? And what is our designated switch, right? Our designated switch, right, is our switch that is connected to another switch, another switch that is not the root, right? So they share an Ethernet segment, right? And what they're doing, right? They're battling for who's the next runner-up, right? Who's the next runner-up to forward traffic, right? And to not block any ports. Okay. And so designated switch, right? Those ports will be in a forwarding, right? And they have ports, port roles called designated, right? And they're going to be in a forwarding state. So it's very important to understand what a root switch is, what a designated switch is, right? And what a non-designated switch is, which of course would be switch 3, okay? Because of course we have to block on one of its ports that's connected to the designated switch, right? Just so we can have a functioning spanning tree topology, okay? So with that being said, we are going to stop here. I feel comfortable stopping here. Please read as much as you can. Go even further than I am. I'm going to explain this the best way that I could. It is a lot of information within spanning tree, one of the hardest topics within routing and switching. If you have any questions, please reach out. And I will see you guys in Lab Fun Day tomorrow. You guys have a great day.